Hi everyone, this is Melissa, and welcome to Chapter 14, Algebraic Thinking, Generalizations, Patterns, and Functions. It is difficult to find an area of mathematics that does not involve generalizing and formalizing in some central way. There are number, place value, basic facts, and computation, proportional reasoning, measurement, geometry, and data analysis, all of which include algebraic thinking. Algebraic thinking pervades all of mathematics and is essential for making mathematics useful. That being said, although I included slides that encompass all grades, I tried to target 4th and 5th grade specific instruction in my narration. Algebraic thinking or algebraic reasoning involves forming generalizations from experiences with number and computation, formalizing these ideas with the use of a meaningful symbol system, and exploring the concepts of pattern and functions. Both 4th and 5th grade standard number 2 are dedicated entirely to the concepts of algebraic thinking, that is, generalizations, patterns, and functions. If students are to become successful in algebra, which is more abstract and symbolic, daily discussion and explaining of numerical situations is vital. Exploring numerical situations rather than just computing is an effective way to infuse algebraic thinking and strengthen understanding of numbers, not just in addition, but all the operations and with all types of numbers. For example, 7 monkeys want to play in 2 trees, one big and one small. How many different ways can the monkeys play in the 2 trees? Students will think about the problem and the pattern and be able to say when the number of monkeys in one tree goes down by 1, the number of monkeys in the other tree goes up by 1. Look for patterns when exploring the hundreds chart. In connecting arithmetic to algebra in the operations, you can ask students, what did I add to get from 72 to 82, from 5 to 15, from 34 to 44? When students stop counting and note the generalized idea that they are actually adding 10 and moving exactly 1 row down, they are deepening their understanding of number concepts and generalizing the idea of what plus 10 looks like. When skip counting, which numbers make diagonal patterns? Which make column patterns? Can you describe a rule for explaining when a number will have a diagonal or a column pattern? If you move down 2 and over 1 on the hundreds chart, what's the relationship between the original number and the new number? Is this true for any pair of numbers that have this relationship? Find a value on the hundred chart, add it to the number to the left of it and the one to the right, then divide by 3. What did you get and why? I added 52 plus 53 plus 54, and I got 159. Then I divided it by 3, and I got 53. One of the most interesting and perhaps most valuable methods of searching for generalization is to find it in the growing pattern represented with visual or concrete materials. The border tiles problem is a good example. Have students use color tiles to build an 8x8 square representing a swimming pool with different color tiles around the border. The task is to find at least 2 ways to get the number of border tiles without counting them one by one. Another fun interactive tool I found to help students explore the border tiles problem is the website planyourroom.com. Students can input their room dimensions, such as 8x8, and click Start. Perhaps one reason that students are unsuccessful in algebra is that they do not have a strong understanding of the symbols they are using. Click the button for a silly little video. A common misconception is that the equal sign means, and the answer is. The equal sign does not mean, and the answer is, yet some presented expressions look this way. For instance, 5 plus 7 equals, and the answer is 12. Or 45 plus 61 equals, and the answer is 106. The equal sign means the equivalent relationship. It is important to ask students to find an equivalent expression, such as 5 plus 7 is equivalent to 6 plus 6, or 45 plus 61 is equivalent to 44 plus 62, or 4 times 6 is equivalent to 8 times. One meaningful use of symbols lesson example is to ask students to raise their arms to look like a seesaw. Explain that you have big, juicy oranges, all weighing the same, and tiny little apples, all weighing the same. Ask students to imagine that you have placed an orange in each of their hands. Ask students to imagine that you place another orange in the other hand. Next, with oranges still there, ask students to imagine an apple added to the left. Then say you are adding another apple, which is also going on the left. Then ask them to imagine the apple moving over to the right. This is particularly important activity for students with disabilities who may be challenged with the abstract idea of balancing values of expressions. After acting out the seesaw several times, ask students to write seesaw findings. For example, if you have a balanced seesaw and you add something to one side, it will tilt to that side. And if you take away that same object from both sides of the seesaw, it will return to balance. This is another meaningful use of symbols lesson example, where they use pans and numbers to demonstrate the example with the equations and the expressions. Begin with true-false equations with multiplication, then move towards open sentences. Here are some suggestions for helping students with the equal sign. True-false sentence examples look like this. Students are to decide which of the equations are true and which are false. Ask students to make up their own true-false sentences to share with a partner. After true-false sentences, you would use open sentences, and they look like this. 7 times 3 equals 3 times blank. 6 times n equals 3 times 8. Ask students to decide what number can replace the blank or the letter to make the sentence true. They should be ready to explain. Even in the primary grades, you can use letters instead of a box in your open sentences, such as the letter N can stand for the missing number. Ask students what the number should be to make the sentence true. Here is a variable example. Gary ate 5 strawberries and Jeremy ate some too. The container of 12 was gone. How many strawberries did Jeremy eat? Although students can solve this problem without using algebra, they can begin to learn about variables by expressing it with symbols. 5 plus s equals 12. The problems can grow in difficulty over time. Students need an understanding of how to apply mathematical properties and how to perceive equivalence as they simplify. Correct the following simplification and explain your thinking. 2x plus 1 minus x plus 6 equals 2x plus 1 minus x plus 6. However, the minus sign carries to both numbers in the parentheses. Therefore, the simplified equation should look more like this. 2x plus 1 minus x minus 6 equals x minus 5. Variables can also represent more than one missing value. Here's an activity suggestion. If you have $10 to spend on 2 granola bars and $1 fruit rolls, how many ways can you spend all your money without receiving change? Show your thinking. To begin exploring this problem, students record data in a table and can look for patterns. They notice that when the number of granola bars changed by 1, the number of fruit rolls changed by 2. This representation would look like 2G plus F equals $10, where G is the number of granola bars and F is the number of fruit rolls. It is also important to include decimal and fraction values in the exploration of variables because students struggle most with these type of numbers. The second example shows if you were buying $1.75 pencils and $1.25 erasers from the school store and spend all of the $35 you had, how many combinations are possible? What equations represent the situation? Show your thinking. Making structure of the number system explicit. Be sure students can connect the examples to general ideas and the general ideas back to examples. This is the distributive property, and it is perhaps the most important central idea in elementary school arithmetic. By 3rd or 4th grade, students should be challenged to translate verbal conjectures into open sentences. For example, in learning the multiplication facts, students might conjecture that if they have a product, like 5 times 8, they can split up the 5 however they like and multiply its parts by 8, and then put it together. 5 can be 3 and 2. So, 3 times 8 plus 2 times 8 is equal to or equivalent to 5 times 8. Using a rectangle table can help clarify and justify the solutions. Teachers must guide students to generalize rather than memorize the properties to use them effectively. Students need to reason through ideas based on their own thinking rather than simply relying on the word of others. The sum of 2 even numbers is even. The sum of 2 odd numbers is even. The sum of an even and an odd number is always odd. Now let's figure out a way where we can demonstrate this and know this rather than just believe it because the teacher said it. One activity example is broken calculator. Can you fix it? Question 1. If you cannot use any of the even keys, 0, 2, 4, 6, and 8, can you create an even number in the calculator display? If so, how? If you cannot use any of the odd keys, 1, 3, 5, 7, and 9, can you create an odd number in the calculator display? If so, how? In question 1, you can create an even number in the calculator display by adding 7 plus 7, which is 14, and that's an even number. You cannot create an odd number in the calculator display by adding even numbers. So 2 plus 2 is always going to be 4. 4 plus 4 is 8. Even numbers, when they're added together, are always even. So you're not going to get that equation to work. Students can explore patterns that involve a progression from step to step. These are called sequences or growing patterns. Students are likely to see patterns in different ways. Some may examine the physical pattern to see what is changing. Determine instructional goal to determine requirements, either verbal representation or symbols. Graphs of functions are another aspect of algebraic thinking. Graphs provide visuals that allow students to readily see relationships between growing patterns. For example, ask students to discuss how to get from one coordinate to the next, up 6 over 1, and then ask how that information can be found in the table. Second, identify a particular point on the graph and ask what it tells about the pattern. See if you can answer the following questions, which you can also post to students to help them understand the graphical representation of the function. How does each graph represent each of the string patterns in the following graph? Why is there not a line connecting the dots? Why is one line deeper than the others? What does this particular point on the graph match up to in the model and the table? For number 1, this graph represents the number of tiles needed to cover the perimeter distance. For number 2, there is no line because there are no solutions between the points. They are not connected. Number 3, because the hexagon shape is smaller or shorter than the other two, you will need more tiles to cover the same perimeter. And last, what does this particular point on the graph match up to in the model and the table? Each point on the graph matches the number of tiles the different shapes take to reach a certain perimeter. Because each hexagon is shorter than the other shape, it takes more hexagon tiles to create a perimeter than squares, and more squares than trapezoids. Students need to be able to make connections across representations to understand functions, and the preceding questions or diagnostic interview are a great way to see whether students are able to link the graph to the context, to the table, and to the formula. The focus of the lesson on this slide is using a graph to express the relationships involved in a function. It's designed for students who cannot create a graph to reflect the features of a function that has been described verbally. So here we would have students sketch a graph for each of these situations, not using numbers or formulas to represent what the graph looks like. Graphs are one of the most powerful representation tools in math. The ability to deeply understand functional relationships is dependent upon both interpreting a graph to describe a function and creating a graph to describe a function. Generalizing about change can help students understand the situations that the functions represent. It is fun to have students sketch their graphs without identifying which situation they've selected, no labels on the graphs. Then they display them on a projector. Let students examine the graph to see whether they can determine the matching situation. These are the graph examples from the previous questions. And for example, the height of a thrown baseball from when it is released to the time it hits the ground. This is what that example would look like. Notice that the analysis of the graphs focuses on how the graphs increase or decrease and how rapidly or gradually. Linear functions are exampled in graphs. They are a subset of growing patterns and functions which can be linear or nonlinear. A major focus of middle school math and growing patterns in elementary school tend to be linear situations. Therefore, linear functions are the focus in elementary math education. Key considerations that will lead students to feel empowered to do algebra are: emphasize appropriate algebra vocabulary. It is the practice of consistently using and having students use appropriate words for situations. Create word walls and keep a journal of the terms so the students can have examples of the words that they're using and the appropriate use. Teach independent variables and dependent variables explicitly. The independent variables are the step number or the input or whatever value is being used to find value. The dependent variable is the number of objects needed, the output, or whatever value you get from using the independent variable. You also have discrete and continuous. Even in elementary school, the discussion of the functions, especially the graphical representations, should include a discussion of whether the points plotted on the graph should be connected or not and why. When isolated or selected values are the only one appropriate for a context, the function is discrete, so it's not connected. If all values along a line or a curve are solutions to the function, then it is continuous or connected. Connecting representations. First, students must understand the connection between each representation. Teachers must pose tasks and questions that help students make these connections. And that is the end of Chapter 14.